Greetings, Alliance Chemistry Team. Commander King here. Today we're looking at, not lithium, whether sodium or aluminum can create a better gas. In other words, which one is easier to remove an electron from and will be more reactive. I've written the electron configurations here. This 1s2 is a little bit off. 1s2, 1s2. And I want to now figure out how to make an argument for which will be easier to remove an electron from. Okay, and hence more reactive in this case. So I've got the electron configuration. I'm ready to draw the Bohr model. I've got my Bohr model. I know sodium has 11 protons. And, there are 2 on the first ring, 8 on the second ring, and then 1 on the third ring. And similarly with aluminum, there are 2 more electrons for 13 protons, 2 electrons, 8 electrons from the 2s2 and 2p6, 2 plus 6, and then 3s2 and 3p1 on the third energy level, 3 electrons. Okay. So looking at these, I'm like, all right, well, I can't really tell from the size right now. But I could make an argument once I know the effective nuclear charge. So if this is step 2, let's take a look at step 3. I want to calculate the effective nuclear charge. Let me just locate these on the periodic table, by the way. Na is right here, and Al is right here. So they're in the same row, but not in the same column. All right. Now, if we recall, the effective nuclear charge is the number of protons minus the shielding electrons. And what the effective nuclear charge tells us is how much pull the electrons out there are feeling from the nucleus. So this electron out here, how many protons does it feel like are pulling on it, essentially? All right, well, let's see. There are 11 protons trying to pull on this outer electron. All right, but there are 10 electrons in the way. In other words, these 10 electrons are blocking these 11 protons from pulling on the third energy level, and so we get an effective nuclear charge of 1. On the other hand here, let's look at aluminum. This time we've got 13 protons pulling, right? All 13 are pulling. And on these valence electrons, we have 3 valence electrons on the outer ring. And between the nucleus and those outer electrons, there are only 10 electrons in between. So there are 10 electrons in between, meaning there's 3, and the effective nuclear charge is 3. So what this 3 means is that the valence electron, essentially, as an estimate, feels 3 protons effectively pulling on it. Okay, whereas this one represents that the valence electron, this one, there are more than one, so electrons, valence electron feels 1 proton pulling. All right, and now we just got to make an argument. Okay, we've got all the facts we need as to which one is it harder to remove on. Well, let's say I'm trying to pull this electron off, right? I'm trying to take this electron from it. And in sodium, in this one here, we've got only 1 proton trying to fight against it, right? Okay, so that's not too bad. I can fight 1 proton and pull that off. It doesn't take much energy. But on the other hand, in this one, I'm fighting against 3 protons. So 3 protons with their positive charge are pulling on that negative charge and pulling against me. Well, which one is it going to be harder to take it from? The aluminum, right? Because there are 3 protons pulling. So if I want to, really pick on an atom here, I would pick sodium. Easier to remove an electron from because I'm only fighting 1 effective proton that's pulling. So I'm going to say that sodium is easier to take an electron from. And why is that? Well, because it has a lower effective nuclear charge, which means the valence electrons feel less pull from the nucleus And that makes it, just drawing an arrow here, easier to remove. And that's it. So when I'm comparing across the row, really the key factor here is the effective nuclear charge. Okay, until next time, King out.